till now we have discussed about the processors and the processes and the process management techniques, and we have also seen that what are the problems that we normally face in process management, say for example critical section problem, deadlock problem, and we have discussed about what are the possible solutions to those problems that are concerned with process management. Now today let us discuss on the other part of a computer system, because as we have said that a computer consists of the CPU. So when we talk about the process management, it is mainly the CPU that is concerned. That is how the different user processes will be executed by the CPU. Among the other components, you have the memory, you also have the input output devices. Okay. So the operating system has to address the problems of all of them, the CPU as well as memory as well as input output devices. So today we'll start discussion on the management of memory. So we'll discuss something on memory management. So in the earlier system, or whenever we want to build a dedicated system, a computer which is meant for performing a dedicated task, it is not a general purpose computing system. In that case, what we can do is we can use a memory model which is called a bare machine. Okay. So the memory model that can be used for building up any dedicated system is called a bare machine. And what is this bare machine? In this bare machine, it is assumed that the system does not have any preloaded operating system, because we are going to build up a dedicated system. That means kind of task that will be performed on that particular system is also dedicated. That is application specific. Okay. So in such cases, we don't have any pre-specified operating system. Whatever task will be handled by that system, or the management of all those tasks will be decided by the designer himself. That means the memory model that will be used in such bare system is a blank memory. There is no operating system preloaded in the system. Okay. So this entire memory is now available to the designer. Okay, and the designer has to decide that where to put the monitor program, and which part will be used for storage of data, which part will be used for used as scratchpad. All those things are to be decided by the designer himself. Okay, and there is no limitation put on the designer. The designer is all in all to decide how the memory is to be arranged. And this is a particular type of configuration which is used mainly for building the dedicated systems. So for example, I want to have a computerized control system controlling a particular plant, say for example some chemical plant or some power plant, where that computer is not likely to be used for development of any program, or it is not likely to be used for any other purpose other than controlling that particular plant. Okay. So if that is the task for which the computer is to be designed, okay, in that case I don't put, say, any of the operating systems like Linux or Unix or Windows NT or NT5, 95, any of those stuff, because I know that the type of task that is specified, and that is the only kind of task which will be performed by the computer, I can go for a dedicated computer system, a dedicated operating system, which will know that what are the characteristics of the different problems that will arise in the control system, and it will try to solve those problems in the most efficient manner. Okay, so that is what again leads to another type of operating system which is called a real-time operating system. Okay, because in case of control systems, your requirement will be the moment some emergency comes, you have to immediately attend that, where the normal way of process scheduling will fail. Okay, however, the type of computer systems that we use, those are not part of bare machine. The computer system that we use, the memory model in that are called resident monitor system. That means a part of the operating system always resides in the memory. Okay. Now, the type of memory that I am talking about here, these are all main memory. This is not a secondary memory. Because I think we mentioned earlier that only when a program or data resides in the main memory, then only it can be accessed by the CPU. The CPU cannot directly access any program or any data from the secondary storage. Okay. So firstly, the program or the data has to be brought from the secondary storage to the main memory, and then only the CPU can access it. Okay. So the type of memory that I am talking here, these are all main memory. This is not a secondary memory. Okay. So in case of resident monitor, the type of memory we have is a part of the memory is always occupied by a part of the operating system which is called the monitor part of the operating system, because every portion of the operating system need not be there in the main memory always. Okay. So for example, a device driver. Whenever I want to take printout of some file, it is the device driver for that driver which is active. However, on a particular system, the users don't take printout all the times. So because the device driver will be needed only when some printout is to be taken, I can load the device driver only when it is needed, only when some printout is to be taken out. During other time, when the printer is not used, I don't have to put the device driver in the main memory, because that will unnecessarily consume main memory. So the entire operating system need not be loaded in the main memory always. Only what you need is a core part of the operating system which is used for say processor management, which is used for this memory management itself. Okay. So these are the portions of the operating system which are frequently used, which are frequently becomes active. So only those part of the operating system can be put in the main memory, and we can call it the monitor part of the operating system, which monitors the system all the times. Okay. Since in the resident monitor system, what is done is the memory, though I am showing this memory as a single block, but it does not mean that the memory consists of a single chip. The memory may consist of multiple number of chips, but we can organize them as a single block in the main memory. Okay. So in case of resident monitor system, the memory is divided into two parts. One part of the memory is always used by the operating system or the monitor part of the operating system, and this portion of the memory is never available to the user program. Okay. And the remaining part of the memory is given to the user for loading the user's program as well as for loading the user's data. So this part of the memory we can call as user area. Okay. So in case of resident monitor, we have two partitions in the memory. One is occupied by the monitor part of the operating system, and the other partition is to be given to the users. Okay. Now, when the operating system is always loaded in the main memory, there is a danger that when an user program is being executed, the user program may try to access something in the operating system area or try to write something into the operating system area when the operating system itself will be corrupted, and that may lead to machine crash. So to avoid that problem, we must have some protection. That means whenever some user program is executed, we must ensure that the user program is not permitted to access the operating system part. Okay. But the operating system, because it monitors the entire computer, so the operating system can have access to the user area. So that means what we have to have is some sort of fencing. Okay. So here we have to put what is called a fence address. Okay. So whenever the user program tries to access the memory, the address which is generated, that is to be checked with the fence address. If the address is less than the fence address, then we know that the user program is trying to access the monitor area of the memory, which should not be permitted. Okay. So whenever this address generated by the CPU while execution of the user program becomes less than the fence address, then there will be an interrupt saying that the user is trying to access an area which is not permitted. Okay. So following that interrupt, the user program has to be terminated. However, if the address is greater than or equal to the fence address, then only it's a valid address and the user program can continue. So always I have to have a check with this fence address. Okay. Now the question is how to put this fence address. There is one option that this fence address can be placed in hardware. See, there is one problem that whenever the user tries to access any memory, the memory address has to be compared with the fence address. Okay. So there are two ways in which this comparison can be made. One is software. I can write a small program that whenever the user program tries to access a memory, there will be a part of the software which will compare this address with the fence address. Okay. But in that case, the process will be very slow because the comparison has to be made by the software. The other option is I can go for a hardware comparator. Okay. So simply I can have a scheme like this. The CPU generates an address. The address will be fed to a comparator. Okay. Other input of the comparator will be the fence address. Okay. And this comparator will check whether the address generated by the CPU is greater than fence address or not. If it is not greater than or equal to fence address, in that case there will be an interrupt and the user program will be terminated. If this condition is true, that is the address is greater than or equal to fence address, then only the addressing is valid and the user program will be allowed to access the memory. Okay. So if I put such an hardware comparator which compares these two addresses, in that case I don't need any extra memory cycle to compare by software the address generated by the CPU and the fence address. That means the process can be very fast. Okay. So here what we will have is whenever the CPU generates an address, the address directly goes to the memory. Parallelly, this is also compared by a comparator with the fence address. Okay. The moment the address generated by the CPU becomes less than the fence address, the trap will be generated, and following this trap, the process will be terminated. So even if the address is directly going to the memory, that is not harmful because the process is not allowed to continue further. Okay. So this hardware comparison can be executed parallelly at the same time when the process is trying to access the memory. Okay. So I can have such a hardware comparator, and the fence address itself can also be built in hardware. That means one of the inputs of this comparator can be tied to the fence address permanently. But with that we'll have a problem, the problem in the sense that if the fence address is built in hardware, that means the fence address is fixed. Okay. So if you have a fixed fence address, there is a danger that if I want to upgrade the operating system, maybe today the operating system takes 40 kilobyte of memory. So my fence address will be set to 40K. But if next day I want to upgrade the operating system, so the area taken by the new operating system is 60 kilobyte. But if the fence address is inbuilt in hardware, which is set at 40 kilobyte, you find that 20 kilobytes of the new operating system is no more protected. Okay, so that comes out of the fenced area. So that is a problem. In the reverse, if the time if the memory taken by the new operating system is less than the previous version of the operating system, in that case, a part of the memory will be fenced unnecessarily, though it can be given to the user. Okay. So both problems exist. To solve this problem, what we can do is this fence address, let us not fix it in hardware, but let us have something called a fence register. Okay. And the content of the fence register will say what is the fence address. And the comparator part can still be in hardware. Right? So this fence address will be stored in a register which we'll call as a fence register. Okay. And whenever you upgrade the operating system, what you have to do is, depending upon the memory requirement of the upgraded operating system, you have to reload this fence register. Okay. Now this reloading of the fence register cannot be given to any user. So there must be some privileged instruction which can be executed only by the system administrator to reload the fence register. Okay. So by having this fence register, we can, and the hardware comparator, we can make this comparison process fast. At the same time, it is flexible, that whenever I want to upgrade the operating system, that accordingly I can set the value of the fence register. Okay. Now, whichever way we specify this fence address, since this memory is partitioned into two partitions, one occupied by the operating system and the other one occupied by the user program, this is mostly suitable for a single user system. Okay, this is not much suitable for a multi-user system. However, this model itself can be converted to a multi-user system if we incorporate what is called a swapping. Okay. So in that case, our model will be something like this. In the main memory, we still have two regions. This is operating system region and this is user region. Okay. And we have the secondary storage. Say, suppose the secondary storage is a disk. Okay. The disk contains many user programs. Let us put this as job 1, job 2, and so on. Okay. At a particular time, if job 3 is a user program which is loaded in the main memory in the user area, that means job 3 is now being executed by the CPU. Okay. By default, this is a single user configuration. I want to convert this to a multi-user configuration. So what I have to do is, whenever the user program job 3 is complete, I have to swap out this into the secondary storage, put it back into secondary storage, and the next job which is to be executed by the CPU, suppose job 2, you swap in job 2 from the secondary storage into memory. Okay. So whichever program is to be terminated or suspended, this may be because of various reasons, as we said, that an user program may become inactive because it may like to have some IO operation, at which point the CPU has to be given to some other process for execution. Okay. The second can be that the program terminates itself. That means it has completed all its operation and the program is terminated. When we say that the process goes to a halted state, then also we have to remove this job 3, J3, from the user area and bring in a new user program in the main memory for execution. Okay. And the third one can be an abnormal termination. A situation like this, that whenever a trap occurs because the user program has tried to access the operating system area in the main memory, then also the job is to be terminated. And once the job is terminated, you have to bring in the next job from the secondary storage into the main memory for execution. Okay. So I can have a situation like this, that a program which has to be moved out of the main memory, that is called a swap out operation, and you swap it out onto the secondary storage. Now there are various things which are to be checked before this process is written back into the secondary storage. One of the conditions that you have to check is that while in main memory, whether the user program was modified or not. Okay. If the user program was modified while it was in the main memory, then I have to write it back into the secondary storage. If it is not modified, in that case a copy of that already exists on the secondary storage, so I need not write it back onto the secondary storage. I can simply override this with the new user program that comes from the secondary storage. Okay, so this is called a swap out operation, and this is called a swap in operation. Okay. So though this converts a single user memory model to a multi-user memory model, but still it has problem, because every swap out and swap in operation means you are going to perform some disk operation or some IO operation. Okay, and generally the IO operations are much slower than the CPU speed. So if I have a multi-user system or multi-programming system with this model, you'll find that even if we are trying to go for multi-programming to increase the CPU utilization or the CPU efficiency, but because of these IO operations, the CPU efficiency will not be as high as we expect. Because until and unless the swap out and swap in operation is complete, the CPU cannot start the next job. So still the CPU utilization will remain poor. Even that problem can be avoided if we can overlap the swap in or swap out operation with the CPU execution. So if we want to do that, what we have to do is, instead of having only 2 partitions in the main memory, we have to go for more number of partitions in the main memory. So the next memory model that we can have is something like this. A partition of the main memory is always given to the operating system, and the user area you divide into 3 parts, into 3 partitions. One of the partitions I call as buffer area 1, this I may call as buffer area 2, and this is called as the actual user area, which contains the program that is currently active. That means the program which is being executed by the CPU. And obviously, as before, we have the secondary storage. Now with this more number of partitions, what can be done is the user program or the active program which is in this 4th partition can be executed on the CPU, executed by the CPU. At the same time, the previous program can be swapped out from buffer area 1, and the next program to be executed can be swapped into buffer area 2. Okay. So this is the kind of configuration that I can have. That a program which has already been executed, that has to be pushed into buffer area 1. From buffer area 1, it will be swapped out, assuming that because we are using this area for containing the active program which is currently being executed by the CPU. So once this program is no more active, it completes its CPU burst, we have to move the program from this area into buffer area 1. Okay, and this being main memory to main memory transfer will be done very fast. The time required for transferring a block from this user area to buffer area 1 will be much less compared to the time required to swap out this buffer area 1 content. Okay. So whenever a process, a job completes execution, I have to move the job from the user area to buffer area 1. A job which is loaded into buffer area 2, that has to be transferred from buffer area 2 to user area 1 when the job becomes active and is executed by the CPU. Okay, so now I have 2 situations. In buffer area 1, I get a job which is to be swapped out. In user area, I have a new job which is to be executed, and buffer area 2 is free. Okay. So next time, while executing the job in the user area, I can swap out the job from the buffer area 1 and swap in a new job into buffer area 2. All these processes can run concurrently. Okay. Though we say all these processes can run concurrently, but it is not so easy, because while execution of the user program will try to access memory, the same memory. The buffer area 1, while swapping out, the process which is swapping out, that will also access the main memory. And a process which is swapping in a new job from the secondary storage into buffer area 2, that is also accessing the memory. Okay, that means the user program 1, the active program, swap out process and swap in process, all of them are trying to access the main memory simultaneously. So there I must have some mechanism so that this memory conflict can be avoided. Okay, but still this can be done, which will be more efficient than this. Okay. Now, again here, as a user program is executed in the user area, I have to have a fence address. Okay, because while execution of a program in this area, I don't want that this program should access any of the other areas, neither in buffer area 1 nor in buffer area 2, of course not in operating system. So I also have to have a fence address which protects all the memory area other than that which is given to the user program. Okay. Now the process can be made still faster in the sense that, as I know that the next program to be executed is in buffer area 2. So instead of transferring the block from buffer area 2 to user area, what I can do is I can simply shift the fence address from here to here. Okay, and let the next program to be executed from this location itself. So I don't need a block to block transfer from buffer area 2 to user area, which again saves a lot of time. Okay. So by now you have got a trend that if I have more and more number of partitions, then obviously I am going to have more and more efficient memory management technique. So every memory addressing will need 2 comparisons. Yeah.
This will be more, more efficient.
Okay. So this suggests that if I have more and more number of partitions in the main memory, maybe that my memory management technique will be more efficient. Okay. So that leads to a concept of what is called MFT. I think we have discussed about MFT in our programming and data structure course. MFT technique, or multi-programming with fixed number of tasks. Okay. So in case of MFT, what is done is the main memory is divided into a number of partitions, not only 3. One partition will obviously be allocated to the operating system. Okay, and the remaining user area is divided into a number of partitions. Maybe these partitions of equal size, or different partitions may be of different size. Okay, in general, let us assume that I have different partitions which are of different size. Each of these partitions can contain one user program or a job. Okay. Now, because I have a number of partitions and different partitions can have different user programs, So the degree of multiprogramming is decided by the number of partitions you have. That means if there are 15 partitions in the user area, I can put 15 different jobs in those 15 partitions. Each of those jobs are ready for execution. Okay. So in this case, switching over from one job to another job is simply changing the instruction pointer content. Okay. So if I change the instruction pointer, suppose earlier the instruction pointer was pointing to some location in this area. That means this is the job which was active. A job containing content in this partition was active. Okay. Now if I change the instruction pointer from this location to this location, in that case the job content within this partition will become active. I don't need any extra swap in or swap out operation. Okay. So the system becomes very fast. But in this case what I need is, because I have got multiple number of partitions, I have jobs which are at addresses less than the partition address. I have jobs which can also be at addresses higher than the partition address. That means to protect every job against others, I must have two bound registers. Earlier I had only one. So one of the bound registers I'll call as lower bound register, and the other one I'll call as upper bound register. And then now the scheme will be for protection that whenever the address is generated by the CPU, if the address is less than the lower bound register content, in that case there has to be tag. Okay, because the address generated by the CPU, it becomes less than the content of the lower bound register. That means the process is trying to access some memory location which is not allocated to it. Similarly, if the address generated by the CPU becomes more than the upper bound register content, then also the process is trying to access some memory area which is not allocated to the process. So now instead of having only one check on the fence register, I have to have two checks. Okay, one with the lower bound register content, other one is the upper bound register content. So I have to have two comparisons. Again, these comparisons can be made in hardware. What modification can be done on this is, since the size of every partition is fixed, if I know that a job is loaded into say partition number 5, I know what is the starting address of that partition. I also know what is the length of that partition. So accordingly, instead of having lower bound register and upper bound register, I can have two other registers. One is called a base register, and other one I'll call as limit register. Because here you find that an address which is not less than the lower bound register content and not greater than the upper bound register content must reside within the limit or within the range base address. The minimum can be base address, maximum can be base address plus limit register. Okay. So now this comparison can be converted in this form, that whenever the CPU generates an address, you compare this address with the limit register content. The address has to be less than or equal to the limit register. Okay. If the address generated by the CPU is not less than or equal to the content of the limit register, then obviously it is trying to access an area the address of which is more than the content of the upper bound register. Okay. So in this case, there will be a trap and the process will be terminated. Okay. If the CPU generated address is less than or equal to the limit value, in that case, this address will be added with the base address and what I get is the physical address of the main memory which is to be accessed by the process. Right? So in this case, obviously the base address is same as the lower bound register, because that is the minimum address that can be generated, assuming that the CPU does not generate any negative address. The address generated by the CPU is always 0 or more. Okay, so that address is compared with the limit register content, because that is also quite logical, because whenever the compiler compiles a particular program, it assumes that the logical address starts from location 0. Okay, so any address generated by the CPU while executing a particular program can be 0 or more. The maximum address that can be generated, that is the limit register content. Okay, so if this address is less than or equal to limit register, then you add the address, because this is the logical address, add this address with the base address, that gives you the physical address in the main memory. And this physical address tells you that which particular location of the main memory is to be accessed. Okay, if it becomes more than the limit, then there will be a trap, because the process is trying to access an area which is not actually allocated to it. Okay. So now, as we said, that the user area is divided into a number of partitions. Different partitions can be of different size. So naturally a question comes that whenever a new job is to be put into the main memory, that means the new job has to be moved into the ready queue, which of these partitions should be allocated to the new job? Okay, so I can have a situation that suppose the first partition is of size 100K, 100 kilobytes. This may be of 40 kilobytes. Next one may be of 60 kilobytes. This one again can be of 100 kilobytes. This one can be of 20 kilobytes. This one can be of 50 kilobytes, and so on. But once I decide that these partitions will have these sizes, the partition size is fixed. Okay. So whenever a new job has to be put into the main memory, I have to find out a partition which can take that job. So naturally, if I have a job whose memory requirement is 120 kilobytes, that job can never be put in this main memory, because I don't have any partition whose size is greater than or equal to 120 kilobytes. Right? However, if I have a job whose size requirement is 50 kilobytes, then that job can be loaded into the main memory, provided a partition of size higher than or equal to 50 kilobytes is available. That is, that particular partition is not already allocated to some other process. Okay. And then I can have so many options. Assuming that all these partitions are initially free and I have to put a job of 50 kilobytes into this partition, I can go for two different kinds of algorithms for this partition allocation. One algorithm is called the first fit algorithm. What does first fit algorithm do? It simply checks this partition serially. The moment it gets a partition whose size is greater than or equal to the required size of the job, immediately that partition is allocated to the job. Okay. So that being the situation, when I have a job whose size requirement is 50 kilobytes, okay, it comes to this, find that first partition whose size is 100 kilobytes is free. So immediately this 100 kilobyte partition will be allocated to job J1 whose size requirement is actually 50 kilobytes. So you find that out of this 100 kilobytes, and because this is fixed partition, the part of this partition cannot be allocated to any other job. Either a partition has to be allocated in full to a job or don't allocate at all. Okay. So this 100 kilobyte partition is allocated to job J1 whose size requirement is actually 50 kilobytes. So the remaining 50 kilobytes is wastage. This cannot be used by any other process. And the process which is allocated to the allocated this partition, that process does not make use of it. Okay. And this partition which is actually allocated but not used and cannot be allocated to any other process is called a fragmentation. And in this case, because this fragmented area is part of an allocated partition, this is called an internal fragmentation. Okay. And this 100 kilobyte partition we have allocated to job 1 based on an algorithm that whenever the first partition whose size is greater than or equal to the required size of the job is available, allocate that partition to the job. Okay. And which I said that it is called first fit algorithm. I can have another algorithm which is called best fit algorithm. What the best fit algorithm will do, that it will check all the free partitions and it will allocate that free partition to this job, which will lead to minimum internal fragmentation. So since the requirement of the job is 50 kilobytes and it checks all the partitions which are free, and if it finds any partition which is free and more than 50 kilobytes but nearest to 50 kilobytes will be allocated to that particular job. Okay. So in this case, luckily we have got a partition which is actually 50 kilobytes. For this, size requirement is also 50 kilobytes. So if you allocate this partition to this job J1, in that case there will be no wastage of memory. That means internal fragmentation which will be generated is 0. But this is a special case which cannot be guaranteed always. But in general, in case of MFT technique, we will have some amount of internal fragmentation. And this is the kind of algorithm that can be used, which is called a best fit algorithm. You try to find out the partition which fits the requirement best. The problem is the complexity of the best fit algorithm is more because I have to search all the free partitions to find out which one fits best. The complexity of the first fit algorithm is less compared to the best fit algorithm. Okay. Now we can lead to another kind of fragmentation which is called external fragmentation. As we said that if I have a job whose size requirement is 120 kilobytes, but I don't have any partition whose size is 120 kilobytes, though all the partitions are free. That means I have a job which is to be loaded in the system for execution. I have a number of free partitions, but there is not even a single free partition which can be allocated to that job. Okay, though partitions are free, but that cannot be allocated. And in such cases, even then it is a wastage of memory. That means we are leading to fragmentation. And in these cases, the fragmentation that is generated is called an external fragmentation. A fragmentation which is not because of non-utilization of a portion of a partition which is allocated to a process. That is an external fragmentation. So in case of MFT technique, we can lead to both this internal fragmentation and external fragmentation. Right? Now obviously to implement this MFT technique, there is some extra information, some information which is to be maintained, and that information is used by the memory management module for allocation of the partitions. Those informations are that what are the partitions in the main memory, what is the size of every partition, what is the starting location of every partition, what is the status of every partition. That means whether the partition is already allocated to a process or the partition is free. Okay. So mainly the starting location of the partition, size of the partition, and the status of the partition. Those are very important for this memory management algorithm which employs MFT technique. So whenever a new partition is to be allocated, it will search only those partitions for which the status is free. The partitions for which the status is allocated, they are not to be checked, because anyway those partitions cannot be allocated again until and unless those are freed by the jobs which are already allocated to those partitions. Okay. Similarly, when a job is terminated and that goes out of the main memory, you have to modify that particular information. Earlier its status was allocated, now we have to make the status to be free. Okay. And this information is maintained in the form of a table which is called a partition allocation table. Okay. So you find that with this MFT technique, we lead to this internal fragmentation or external fragmentation. Obviously, these are the fragmentations. The fragmentations are never desired in a system because this leads to wastage of memory. So we should think of a technique by which the fragmentation can be minimized. And there is a technique which is called MVT technique, or multi-programming with variable number of tasks, that we will see in the next class.
Program, my logical address starts with 0.
Yeah.
So for a single user environment, all you have to do is to add the fence address and then give it to the main memory. How can it be compared with the fence address?
No, for a single user system means, are you talking about the bare machine or
So the
no,
resident monitor.
Resident monitor. In case of resident monitor, a part of the address, a part of memory is always given to the operating system. That is the portion which cannot be accessed by the user program. Okay. So there, I can have two situations. One is if I assume that the CPU generates the logical address, that means the address is to be generated from 0 onwards. In that case, the fence address or the fence register is to be replaced by base address register. So in this case, it is because I replace that by base address register, and I know that the address generated is always greater than 0, logical address. So I don't have to go for comparison. Only one comparison is needed. That is, the address generated does not exceed the limit. But the first one that we said, there I didn't assume that the CPU generates logical address starting from 0 only. The address generated was physical address.